Hello again and welcome to Construction Management 329, Construction Equipment. So today we're going to start talking a little bit about earth moving equipment and soil properties. So we need to know about some of the properties of soil before we start discussing any details on the equipment itself. So things you should have learned in soils class, have you been paying attention? Any mass of soil consists of solid particles with voids in between. Whether it's rock, whether it's sand, clay, any type of soil, it's soil particles with voids in between. And these voids can be filled either with water or air. If it's submerged or under the water table, then the voids are going to be filled with water. Or if it's above the water table and not submerged, then it's going to be filled with air. Just having a look at this graph shows basically what we're talking about. It has solids, and then again, if partially submerged, it's going to have water, and it might have air. All of this may be filled with water if it's totally submerged, and all of this is going to be filled with air if it's not submerged at all. And these can be measured either by volume or by mass. So looking at the volume, we have VT, which is the total volume of that sample of soil, with VS being the volume of solids, and VV is the volume of voids, which can be divided into VW, volume of water, and VA, volume of air. On the other hand, if we measure it by mass, then MT is the total mass. Notice here that MT is not up to the top because air doesn't have any mass. MA is equal to 0. So MT is going to be just equal to MS, the mass of soil, the solids, and MW, the mass of water. If you want to calculate the weight of that soil, the unit weight is going to be the total weight of the soil divided by the total soil volume. So W over V. We get a soil sample, we weigh it, and then we divide that weight by the volume, and that gives the unit weight or the density of that soil. Dry unit weight, however, YD, is going to be basically the weight of the soil solids, excluding the water. So we put it in the oven to dry it and get rid of all the included water. And then we weigh the solids divided by the same volume, which is going to be total soil volume, and that gives us the dry unit weight. The moisture content, which is the amount of moisture in that soil, is going to be calculated as the wet unit weight minus the dry unit weight, again by drying the soil in an oven, getting rid of the water. So wet unit weight minus dry unit weight, which is basically the weight of water, times 100% divided by the dry unit weight. It can range from 0% if the soil is totally dry in a desert or something like that, to several 100%, because in some cases the weight of the water and the volume of the water can exceed the volume of solids themselves. So in this case it can be more than 100%. Water content for most soils is well under 0%, although it can range up to 500% or higher in some marine and organic soils. Soils that can hold a lot of water, or soils that are totally submerged as marine soils. Now, looking at an example for these calculations, excavated material has a wet unit weight of 94.3 pounds per cubic foot, that's PCF, and a dry unit weight of 87.3 PCF, and the embankment will be compacted to a dry weight of 114 PCF. Compacting the soil means getting rid of the voids totally or to a certain level, so getting rid of the air, making the soil particles come closer to each other, and the desired water content is 12%. The net section of the embankment is 113,000 cubic yards. What type of cubic yards? We're going to discuss that in a minute. What is the moisture content of the excavated soil? How many cubic yards of excavation will be required to construct the embankment? And do we need to add water or not? If yes, what's the volume of water to be added? So to solve this example, let's start looking at the input that we have. We have a wet unit weight, we have a dry unit weight, and based from these two numbers, what we can do is get the weight of water, which is the difference between the two, which is going to be basically 7 pounds per cubic foot, and then divide that by the dry unit weight, which is 87.3 pounds per cubic foot, and that's going to give us the moisture content of that soil. Proceeding with the other calculations, as we're going to see in class, would give us the answer to the rest of these questions. Now, since I just mentioned, when we talked about the cubic yards of soil, what type of volume are we talking about? We have basically 3 different types of volumes. We have the bank volume, which is the volume of the soil in its natural state, before disturbing it, before removing it, before excavation, before doing anything to that soil. In its natural condition, that's called bank volume, and it's expressed in BCY, or bank cubic yards. Once we start excavating the soil and disturbing it, what we're going to do is insert additional voids in it. We're going to loosen it. We're going to distance the soil particles from one another. Therefore, the volume is going to increase a little bit. So the material has been excavated or loaded. That's going to give us a loose volume, which is measured also in cubic yards. But in this case, it's going to be LCY, or loose cubic yards. Now, after backfilling, we need to compact the soil to bring it back to some sort of compaction, removing or reducing the voids in that soil. So it's going to be also measured in cubic yards, but in this case, it's going to be CCY, or compacted cubic yards. Looking at these 3 volumes, which one do you think is going to be the largest volume? Of course, it's going to be the loose cubic yards. The medium one is going to be the bank volume, and the smallest volume is going to be the compacted volume, because we try to get rid of as much of the voids as we could, or as desired according to the required or the desired bearing capacity of the soil, and so on. What happens when we excavate the soil? As I mentioned, we insert or we introduce additional voids in it that can be either filled later on with air or with water. So the soil increases in volume when it is excavated, because the soil grains, the soil grains are loosened during the excavation, and air fills the void spaces created. So that is called swelling of the soil, which is that increase in volume. The percent swell is going to be equal to the loose volume minus the bank volume divided by the bank volume times 100%. So we say, for example, that the swell factor for the soil is 25%, or is 15%, or is 5%. It's based on the difference between the loose volume and the bank volume, which is just the amount of swell, divided by the bank volume multiplied by 100%. Now, looking at different types of soils, for example, if we're talking about rock, what do you think? Which one is going to have a larger swell, rock or clay? Think about it for a second. What do we do? How do we excavate rock? By the way, it's usually going to be through blasting, and it's going to break the rock into basically different sizes of boulders, and these are going to be probably angular. They're not going to be very symmetrical. So what's going to happen is you're going to have a lot of gaps between the soil particles, which are going to be relatively large, which means a lot of air is going to be introduced between these soil particles. So you should expect that the swell percentage for rock is going to be much larger than that for sand or for clay. Clay, very sticky particles. Even when you disturb it, it's still going to keep some of its consistency and some of the cohesion between the different particles. So yes, the volume is going to increase. There's going to be some swell, but it's going to be much less than that for sand or for rock. The percent swell can also be calculated based on density. So in this case, the percent swell is the density of the bank volume, the density of the bank soil, or the bank density, minus the loose density, because again, the bank density is higher than the loose density. Remember that the air does not have any density, therefore the weight of the soil in its bank condition is going to be greater than the weight of the soil in its loose condition per the same volume. So density bank minus density loose divided by density loose. Notice the difference between the two. When we calculated the volume, we divided by volume of bank. When we calculated it based on density, we divided by the density of the loose. So dL is the loose density and dB is the bank density. The opposite of the swell is shrinkage. When does shrinkage happen? It happens when we compact the soil, when we intentionally try to get rid of some of the voids in that soil. So when the soil is compacted, air is forced out of the void spaces. The soil will occupy less volume than it did under either bank or loose conditions, and the percent shrinkage is going to be equal to the volume, the bank volume, minus the compacted volume, which is after compaction, divided by the bank volume. Our datum is going to be the bank volume. The one that we measure to is going to be the bank volume times 100%, where VC is the compacted volume and VB is the bank volume. Now think about it for a second. Which volume is going to be greater, the VC or the VB? Of course it's going to be the VB. The bank volume is going to be greater than the compacted volume. Now again, which density is going to be higher, the compacted density or the bank density? Of course the compacted density is going to be higher because now the soil particles have been compacted, getting close to each other. We got rid of air, which doesn't have any density. So for the same volume, the density of compacted soil is higher than the density of the bank volume, bank soil. So that's why here when we divide, when we get the shrinkage, we divide by the density of the compacted soil. So density of compacted minus density of bank divided by density of compacted times 100%. Swell and shrinkage are properties of the different types of soils. So depending on the type of soil, it's going to have its own shrinkage percentage and swell percentage. And these are going to be usually given to you through the report, the geotechnical report produced by the geotechnical engineer or the soils engineer, who's going to do all the lab tests, including the dry density, wet density, dry volume, wet volume, moisture content, bearing capacity. All of these different types of tests, which you should have learned about in the soils class, are going to be conducted by the geotechnical engineer. You do not make these calculations, but you should be able to make an interpretation of these different calculations and know exactly how is that going to affect the volume of soil that has to be removed from the site or imported to the site, and so on and so forth. So again, I believe this graph shows what we're talking about. If we had 1 cubic yard of bank soil in its natural condition, when we break it down and try to transport it away from the site, the volume is going to increase. So here you can see that 25% is going to be our swell factor, because the 1 cubic yard became 1.25 cubic yards, although we should say that this is going to be BCY, bank cubic yards. This is going to be LCY, loose cubic yards. When we try to backfill with the soil and bring it back to its almost natural condition, even better than the natural condition, we're getting rid of a lot of voids. So here we're going to have the compacted volume is going to be 0.9, therefore we have a shrinkage factor or compaction factor of 10%, which means the 1 cubic yard ended up being 0.9 cubic yards. So if we need to backfill about the same volume of soil, we have to import additional soil to cater for the difference of 10% that resulted from that compaction. To convert between the different volumes, to convert between bank and loose and compacted and so on, so the volume bank is equal to volume compacted times 100% over 100% minus percent shrinkage. The volume loose is the volume compacted times 100% plus swell percentage. This is expressed as a percentage. So for example, if you have swell percentage of 25%, this is going to be equal to 25. So this is going to be times 100 plus 25, 125, divided by 100% minus percent shrinkage. So this way we can convert. If I know the compacted volume, I can get, and knowing the swell and the shrinkage percentages, I can get the loose volume, and I can get the bank volume also. So you can convert between these three different types, knowing these two equations. To look at an example here, a soil weighs 1,960 pounds per loose cubic yard. Now notice that this is loose cubic yard, which means when we excavate it, when we disturbed it, after the excavation, that was the weight as it was measured. And it's not in its natural condition, it's 2,800 pounds per bank cubic yard, and compacted, now again, the density is going to increase, so the weight per unit volume is going to increase, 3,500 pounds per compacted cubic yards. How many bank cubic yards and compacted cubic yards are contained in 1 million loose cubic yards? Again, based on the equations that we just learned, to get the bank volume, we multiply the loose cubic yards, the loose volume, times the loose density divided by the bank density. And that gives us 700,000 bank cubic yards. To get the compacted volume, we notice that it's going to be even much less than that, which is going to be 560,000 compacted cubic yards. That shows you the amount of compaction that this soil is going to go through. So that tells you how much more soil do we need to bring from out of that site just to compact, to fill the holes that resulted from the excavation. Another example here, in building a parking lot for a new school, 10,000 compacted cubic yards are required for the fill. The contractor has selected the source for the fill and found out that the bank density is going to be 2,800 pounds per cubic yard. What kind of cubic yards in this case? Well, the question is given here. The answer is given, bank density. So this is going to be bank cubic yards. The loose density is 2240 pounds per cubic yard, also loose cubic yards. And the compacted density is 3415 pounds per cubic yard, in this case CCY, compacted cubic yards. He plans to excavate the fill material with a wheeled loader and load dump trucks that will haul the soil to the construction site. What is the percent swell for the fill material? What's the percent shrinkage for the fill material? How many loose cubic yards must the contractor haul in the dump trucks? How many bank cubic yards must the contractor excavate with the loader? So again, from this information we can answer all of these different questions. First step is to calculate the swell and the shrinkage from these different numbers using the equations that we already learned about. So the percent swell is 25%, the percent shrinkage is 18% based on these two different calculations. So how many loose cubic yards must the contractor haul in the dump trucks? The volume loose is going to be the volume compacted, again using the same equations that we learned about before, times 100% plus percent swell divided by 100% minus percent shrinkage. So it's going to be 10,000, that's the compacted volume that we know about, times 125% divided by 82%. And that gives 15,224 loose cubic yards. So when you measure the soil on the trucks, which is going to be loose, this is the volume that you need to bring to the site. How many bank cubic yards must the contractor excavate with the loader? Again, to achieve these loose cubic yards, so it's going to be that volume. 12,195 bank cubic yards are going to produce 10,000 compacted cubic yards. And that's the end of this lecture about soil properties.